you have not so much information about the noise. This is the problem. And so it depends how much you are visit sensitive or not, how much you trust your sample. As we will see, most of the analysis that we will do later are somehow in the worst case just to be robust. Of course, you can be more neutral in this, so you can have different results. But it doesn't change the way so much. Okay, so now we have said that there are 3 steps in any supervised learning problem. So we have said that the loss function, then we have said that there is the hypothesis space and the optimization procedure. And so now one can wonder what are the choices for each one of these steps, how many alternatives. The answer is plenty of them for any of these steps. And actually, you know, machine learning is a very fast-growing field. Every day, new algorithms, new techniques. But the core, the principles, are few and are stable. The techniques, many, but when you have many of something, it means that there is, as I've already told you, there is no a clear winner there. They are all alternatives, plenty of them. Because the problem is hard, this is the reality. And so there is space for everyone who just try and produce one. And okay, so what are the points that are in discussion for any algorithm? We have said the hypothesis space. The hypothesis space says how do you represent your solution? How you model the function that maps input to output. This is the representation that you want. And there are plenty of them. Evaluation. Evaluation is about the loss function in the end. When I give you, suppose that now I give you an algorithm. How do you evaluate its performance? When you test, when you train, it's the loss function. What is an error for you, for your problem? There are plenty of loss functions that takes into account the different solutions. And then there is optimization, as we have said. Once you have chosen the representation, you have to choose the loss function, so how to evaluate, you have to find the best solution. Okay, and actually what happens is that for what concerns representation, you have many different approaches. Okay, we will look only at a few of them. Actually, we will only focus on linear model. We will say something about instance-based approaches. We will not talk about trees. We will only mention them. We will not talk about them because they are covered in the data mining and classifying course, even for the set of rules. And again, for what concerns graphical models and neural network, we will not deal in this course, but they are covered in the soft computing course, to some extent at least for graphical models. We will deal with Gaussian processes, support vector machines, and model ensemble. But what I want to stress is that it's not that important, the technique. Okay? It's just enough to have a few of them. Because actually there are thousands of them. And this makes no sense actually to know every one of them. But at least the categories, the macro categories, and then what are the principles. For what concerns the evaluation, again, you can have many different metrics that can be considered according to your problem, if you are in a classification problem, regression problem, according to how much you are risk averse or risk neutral. You have many different solutions. Here we will mention the most commonly used, but actually you have to pay attention. There is not only the ones that we will see in the course that are the most commonly used. According to your problem, maybe you have to change your evaluation function. What determines the success of an evaluation function? In most of the cases also how easy it is to optimize this evaluation function. Because maybe for your problem, you know that there is a perfect evaluation function, but that is very hard to be optimized. And so maybe you prefer something not optimal for your problem, but easier to get. Yeah. So there is also a trade-off in the choices of the representation, on the evaluation, and also for the optimization you have a trade-off. Because, again, you know, you have done optimization courses, I suppose, so you have seen you can have different approaches to optimization, and these different approaches comes with pros and cons in terms of what? In terms of computational requirements that they have, and also possibility of being accurate or depend on the starting point, local minima. There are many things related to this. Again, you will have for each one of these representation, evaluation, and optimization, make a choice. And in order to take a choice, you need to know. Because if you do not know everything, your choice is just by faith, just by chance, okay? And it's not a good way. You need to know pros and cons of the different approaches, okay? And then, like engineers do, take the choice that optimizes your. So, don't become a fan of any technique. It's the worst thing that a machine learning scientist can do. Becoming a fan of some particular technique. Because as we will see, this is doomed to fail sooner or later. Of course, since we are empirical beings, when you will try your experiment, maybe for your problems, it may happen that some technique performs better than other. And so you say, oh, this is much better. Forget all the others. I will go with only one hammer, and any problem will be the same nail for me, and always use the same hammer. This is not good, definitely. Because any problem has its own peculiarities. Okay, finally, just a brief mention to some dichotomies, common dichotomies in the machine learning community. What are dichotomies? Again, as in any community, there are parties. And there are no elections in this case, like you have seen, but there are parties again, and they fight. They hate each other. There are change of parties, of many people, in common. But it's true. It's really because unfortunately you become fan of something. Or what is important is to know the families. And then you will go on one party or the other party and ask for what you need. The one first dichotomy is between parametric methods and non-parametric methods. This is about the representation that you want to use to learn. Parametric means that the model that you want to represent here is a parametric function. So it's a function with some parameters. For instance, neural networks are parametric models. You have neurons with weights, okay? They are parametric. You want to find the parameters of the model that minimize your loss function. Non-parametric methods are methods that whose complexity is not given by the parameters, the function shape, but but changes according to the data. For instance, trees, decision trees. Decision trees build their representation according to how many data they have. If you have a lot of data, you can build very complex trees. If you have few data, they adapt. We will see also the kernel regressions, the Prometheus machine, they are all non-parametric together. But we will see that there is a strong duality between parametric and non-parametric methods, in the sense that you can always represent one method the other way around. That probably is not the best thing that we can do. But just to see that they are two different words, but have a very strong point of contact. Then, oh, this is very big fight between people that are from the frequentist world and Bayesian people. They hate each other deeply. And okay, probably you know everybody the Bayesian theory, so the Bayes theorem, all that stuff that comes together, and the frequentist approach, that instead of adding some prior distribution and then updating with the data that you observe and change this distribution, simply take the data and compute statistics directly over the data without any prior information. Two very different worlds. Again, here we will see that there are points of contact, but usually people from one side that say, no, all the other stuff is rubbish, it's not important, and vice versa. We will see some of this. We will see both frequentist and Bayesian approaches. Of course, we have not plenty of time to go into depth of these differences. Another interesting differences between generative and distinctive approach that currently in these few years is becoming more important because generative approaches in the last years are becoming more prominent in machine learning. While some years ago, discriminative approach was the standard, and generative approach was only something fancy that was used by a few people. Currently, nowadays, generative approaches are taking place more and more. We will see later on what are generative and distributive approaches. And then what we have just talked now, the difference between empirical risk minimization approaches and structural risk minimization approaches. What's the difference here? What is empirical risk minimization? Empirical risk minimization is just what we have said a few seconds ago. I want to minimize the error over the samples that I have collected. This is an empirical risk minimization. The term risk is for loss. So you want to minimize the loss function, considering only the error over the samples. Okay? And what is a structural risk minimization? It's just to account also for the size of the hypothesis space. Actually, at the very end, it's very uncommon to have a pure empirical risk minimization algorithm because it's too weak when you have a few samples. Actually, all of the approaches, directly or indirectly, take empirical risk minimization and try to combine it with some concept for structural risk minimization. It's different the way in which they combine these two information. So the error on the samples and the size of the hypothesis space. If it is made explicit, the size of the hypothesis space, you talk of structural risk minimization. If it is implicit, as we will see, is more commonly referred as empirical risk minimization. Okay? So these are just, I think, concepts. Now, we can start with the first approach of supervised learning. Let me.
Sicuro lì a sedere. Si vede sia comunque. Caldo, una serie standard per comunque. Oh, io sono passato dal lecture 1 al lecture 2. Mi sono perso una lecture. Credo già staccato il connettore.
Okay, so now we start from the simplest case, that is the case of linear models. Just start easy. But as we will see, as I told you before, not just because they are called linear models, that means that they do not work. Okay? As I told you before, linear models can be much better than Bayesian trees, the supervised machine, the neural network. It depends on many things, but it can happen. And during the course, this will be clearer and clearer, I hope. Okay. Let's start with the problem of linear regression. Now we will start with the regression problems. Then next week we will see also classification problems. But start with the regression problem. So where now the output is continuous. And we will talk about linear regression. So again, what's the goal? The goal is the following. You have some input space, X, that can be a vector space, of course, because you can have multiple inputs, data, and an output space, T, that again can be a vector space, or for instance, in this case, it's only a scalar space. But you have input and output. And you have some samples that has been collected for your problem. Again, what you want to do is to find a model that relate X. For instance, in this case, the red line. Suppose that the red line is the model that, with some noise, has generated the blue dots. Okay. Your goal is to learn this model. Of course, when a regression problem happens, many different problems. Anytime where you have to fill the knowledge that you do not have. Here you see some application domains, for instance, finance. Okay, you want to predict the price of some stock market. You have some input data, and you want to predict the price. The price is a continuous value. You want to predict this value. Or the age of a web user. Okay, again, you have some information about the navigation pattern, about the history of the user, and maybe, but you want from this data to predict the age. Again, you have some input and you want to predict an output. Okay. Of course, maybe you have data from some user of which you know the age, and you want to be able also to predict the age of other users without this data. And you have many other fields. There are thousands. So what is the idea of linear models? The idea of linear models is simply to have models that are a linear function of what? Of not the input data, as it is in this case. This is a linear model, for sure. But the important thing is that linear models are models that are linear in their parameters. So a linear regression model is a function where the parameters of the model are all linear. What means this? It means that the parameters do not appear at the square power, are not multiplied each one, there is no logarithm over the parameters. Okay? So in this case, suppose that you have input x. Okay? And you want to predict and to do this, you use an hypothesis space that has linear model of x. So for instance, so you want to build a function y of x. And this function will have some parameters. For instance, w1 parameter times x input plus, let's say, w0, another parameter. Okay, this, if x is scalar, I'm supposing x is scalar, and also the y function is scalar because t is scalar. Okay, this is a simple linear model. You have two parameters in this model, w0 and w1. Okay. With this model, okay, you are able to represent any line in the input-output space. This is a linear model, but pay attention. If I do this, so I take x squared, this is again a linear model, because x squared is not linear, but x squared is not a parameter. w1 and w0 are the parameters. And y is still linear in w0 and w1. Okay, so this is again a linear regression model. This is again a linear regression model to take the exponential of x. Because again, the important thing is that w0 and w1, which are the only two parameters of this model, are, so y is a linear function of w0 and w1. Okay. This will be very important as we will see. But for now, let's keep things simple, and let's keep that we consider also the input variable linear. So we are only able to produce models that are linear in the input variable. Okay? But again, it's very important a linear regression model, okay, is linear in the parameters, not in the input variable. Because if you have a model that is linear in the input variable, this is true that it's a very strong assumption. But having the assumption that it's linear only in the parameter is not so strong, as we will see in a minute. Now, why is it interesting to consider linear regression? Interesting for the following. First of all, linear problems can be solved analytically. What means? It means that you can have a closed form solution. And this is very cool. Why is cool? It's cool because given a problem, except some degenerative case, you have only one solution. If you go to nonlinear problems, usually, what happens is that you have multiple solutions. Why? Because with linear problems, with most of the loss functions, what means that you have a closed form solution? It means that the loss function has only one minimum, and this minimum can be computed analytically. In other cases, or you have only one minimum, but it cannot be computed analytically. So you need to use some gradient approach to reach the minimum. And this is still good. But in many other cases, you have multiple minima. Things like neural networks. If you use these complex models here, what happens is that you have no more only one solution to the problem. You have probably one solution that is the global optimum. But finding the global optimum is very hard because you have a lot of local minima. And if you have never tried to train a neural network in your life, it's a nightmare most of the times because it's very hard to optimize. It's very powerful, but it's hard to train. While here for training, you have no problem. You have analytical solution for the best hypothesis in your space. So this is very cool. Many other approaches have been built over linear models. For instance, support vector machine that was, before the deep learning area, was the state of the art for classification, actually is built starting from linear concepts, then bringing them to more complex scenarios. But is the fundamental brick of many other approaches. And of course, as we have said, having a model that is linear in the parameter doesn't mean that it's linear in the input. So with a linear model, you can approximate any arbitrary complex function, provided that you give what is called the basis features of the problem, as we will see. Okay? So what is important is that with the linear regression model, you can, in principle, approximate even very complex functions, not only linear ones. Is this clear? Are you following? You're so silent. Falling asleep. Loaded. Okay. So this is the idea in the general case. If you have multiple, if the input space is a vector space, so you have that, you have a different component of x, because x now is a vector. And so then we have this model. We can see that, as we have seen, there is a parameter that is just the intercept. And then you have the summation of some parameter wj multiplied by the j component of the input vector. And so you can write this by writing the scalar product wt x, where x is defined the following way. So the first component is 1, because it needs to be multiplied by w0. And then you have w1 times x1, w2 times x2, and so on. Where d is the number of parameters. So w is a vector of size d, x is a vector of size d, D, the dimensionality of the input space is D minus 1. Yes? Okay? So D is the size of the parameter vectors, while D minus 1 is the size of the input vector X. Good. Now go back to the visualization that we made last time and also at the beginning of this class. We have an hypothesis space. So we have the space of all the function f. Then we have the hypothesis space. This space now is the set of linear models of this kind. Are also linear in the input space. So here we have our hypothesis space. That is a subset of all the possible functions that we have. Perfect. Now, here you have the following. W0, W1, now we are supposing to have only 2 parameters, so D equal to 2. This is the hypothesis space that we are representing with these parameters. So a point in this space, W0, W1, this point here, corresponds to a model in the input-output space, that is this red line. Okay, so a point in this space is an hypothesis. An hypothesis is a candidate model. So you can go in the input-output space, take this point, and draw the model in the input-output space. If I take another point, I take another model. And you go on. You have different hypotheses that are related to different models. Again, what you want to do, you want to find the model that minimizes some loss function. Okay? So now, for now, we are only doing what? We have defined the hypothesis space. This is our hypothesis space. That are all the linear models that we have in the input-output space. Okay? But we have said that we need another thing. We need the loss function to choose which is the best model here, which is the best model in this problem. So, loss functions for yes.
Here, one point is an hypothesis,
Yeah.
and it corresponds to one model.
One model.
Okay.
Each point here, what means the point here gives the value of W0 and the value of W1. Once I have the value of W0 and W1, I plug the values in the model, I have a function. The red line is the function. Correspond. Okay? You want to find the model with the best performance. Well, the best performance is given by the least loss function. So we have to define the loss function. Let's reason about the loss function for regression. Okay. So to do this, we need to define the loss error. What is the loss error? It's a function that takes as input t, that is the output value of the target model, and y, that is what your model predicts about this value. You have to define what you do for this loss function. And then, once you have defined how you measure the error between t and the prediction of your model, you usually compute this one, this metric. That is the expected value of this loss function with respect to a distribution. Which distribution? P. What is P? If you look at here, you have that P is a function of the input and the output. what is P is the distribution of that you are using for sampling beta. P is the distribution under which you want to optimize your model. What is this? It is not said that you want to have the same accuracy along all the input space. It may happen that you want to give more importance to error in some regions and less importance to the error in other regions. So P, what is actually P? P is the distribution that you expect to have over test samples. So samples over which you will be asked to predict the value in the future. So your performance will be evaluated later on under P. Okay?
But it's the distribution.
Is the distribution of, let's say, the future samples. So the samples that will be generated in the future after you have trained your model. Because you train a model, then you will use this model, yeah, right? And this model will be used in some scenarios that are distributed according to P.
Is this distribution a degree of freedom in the hands of the user?
Actually, yes and no, in the sense that this is given by the problem, but usually it's not known, and so you can make some hypothesis over this. But actually it's not really under your control, because the distribution of the samples over which you will be asked to work is not of your choice, usually. It's the problem that produces samples, and you have to say, for instance, the age. You have customers, and you have to predict the age of these customers. But the distribution of the data that describes the customers exists, but usually is not perfectly known.
It's the distribution of the error or the distribution of the function?
No, it's the distribution of the samples that you will see in the future. Usually, you assume what? That the distribution of the samples that you use for train is the same as the distribution of the samples that you will use in the future. This is the common assumption. That is not always realized, and this is one of the problems of misevaluation of the performance of your approach, because you assume that in the future you will have samples with the same frequency as in the training set, but then the distribution changes.
So it's only half an hypothesis. Like we extract the distribution from the training set, and then as an hypothesis we predict having the same for the test set.
Yeah.
But the distribution is empirically extracted from the training set.
Now we are a step before this. We are saying we define this as a loss function, and actually this loss function works for any probability. Okay, so what I'm saying is give a probability distribution of the samples P. Then you compute the loss function as follows. Then what you use is later. Okay, but we want just to define what is the expected loss. The expected loss is integral over input space and output space of the probability of having this particular combination of input-output multiplied by the loss that you have chosen for a single point. So it's the expected loss over distribution over input-output of some function. For instance, in regression, the common function that is used is the squared loss. What means where L here is replaced by what? By the difference of t and y, so t the true value, so the measured value. Y is the model, you compute the difference, and you raise at square. This is the expected square loss under distribution P. Yeah.
For a gain.
Yeah.
The probability P or less than P.
Yeah.
probability that I will expect to have, I mean, I will expect to have associating an X to a target.
Yeah.
In samples, not
Yeah.
how many of these kind of samples I will expect to be.
Is the distribution? I am picking a new sample. Okay. What is the distribution from which I'm using? This is the meaning of. So when you get a sample, it comes an input. So again, suppose to make the example of the web user, and you want to predict the age. Okay. You start your system, it comes the first user. He will come with some features, okay, and with an age. Then, user will come with other features and with another age. And you have something from this. This distribution, for example, will depend on the website. It's not the same for. And if you train on a website, and then you use what you have trained on a website, to predict on another website, probably P will be different. And so this will be a problem because there is a mismatch between the loss function that you use to train and the loss function on test. Yeah.
So if I got it correctly,
Yeah.
P is extracted from the sample generated from the model.
It's not extracted. P exists. And
Yeah.
is the distribution from which you sample data.
Okay, but so you choose P,
No.
no?
P isn't the problem.
Okay.
The problem produces data. Usually you do not choose data, unless in an abstract problem. In real world problem, data arrives. The customer of an online shop arrives. In some cases you can choose part of P. For instance, the part of X, in some cases you can do active sampling, it's called. So sampling some points of X. But the part of T is not under your control, because it's the noise. The model plus the noise. Okay, again. We have a distribution over the input-output space that produces samples. Given one sample, we want to compute the loss function of a model Y. And for instance, we can use the square loss. It's not the only choice, but it's a possible, the common choice. And of course, we have to wait by the probability of having the sample, because we want expected value over all the samples, over all the possible samples. Again, this is theoretical definition of the loss function, because practically you do not know P. Usually you have samples. Few samples from P, probably. Okay? But you have samples from that distribution. You do not know the distribution. And so you have to say, how I can approximate this? It's not difficult. An expected value, how do you approximate an expected value? With the empirical mean. Actually, machine learning is replacing expected value with empirical mean. Not much science in that. Okay? In the very end, is that you are doing. Okay. So, if you use this loss function, the nice property that you get, so if you use the squared loss function, the nice property that you get is the following. Is that the optimal model under this loss function is the model that computes, supposing that your model is in the full function space, in this case, so you have no hypothesis space. If you optimize, find the model that optimizes this loss function, what you get is the conditional expectation model. What means that a model that outputs the expected value of t for any input value x. Okay, so what this function, this loss function, tries to make you learn is the expected value of the output variable t given the input x. And this is how it is represented. So, suppose that in In red, okay, you have your model Y. And what is this blue line? This blue line is the distribution of t, so the output value. And what will the optimization of this loss function produce? Will produce a prediction in this point x0 that is the expected value of t under this distribution. So in each input point, okay, you have a distribution that is the marginalization of p fixing x. So take p, fix x. Now you have a distribution only over t, right? Perfect. Now take the expected value of t with respect to p where x is fixed. So x is fixed, you integrate over t with the probability of t given x. And you take the expected value. This is the result. Okay? This just gives an interpretation of what the square loss function will lead. Then probably you will not be able to achieve this. Why? Because your hypothesis space maybe is not able to predict the expected value of t for any input point. Okay? But if you would have an infinite, the full function space and an infinite number of samples, what you will learn is this one thing. Okay? Yeah. Yeah. If this one, yes, actually, P is the joint distribution, right? Between over x and t. If you only fix x and you cut this joint distribution over along t, you get t of t given x. Of course, you need to renormalize everything, but the meaning is that you have to apply the bias theorem between the joint distribution and the conditional distribution. Okay. More generally, we can replace L with the difference between t and y raised to the power q. That in the case of square law, q is equal to 2. But you can make also different choices. So we have said that if you take q equal to 2, you have the expected mean. If you take q equal to 1, you take the conditional median, not the mean, but the median. So the point that splits the 50% of the distribution above and below. And if you take q that tends to 0, what you will predict is tend to the conditional mode. What is the mode? It's the value that maximizes the density. So it's the peak, the highest point in the density. Okay, so changing the loss function, as you can see, you find different solutions. In one case, you are aiming to the conditional mean. In another case, you are aiming to the conditional median. In another case, the conditional mode. And if you make other choices, you are going toward different solution concepts. Okay?
Sorry, I didn't get what happens if we choose q equal to 0.
What?
What happens if we choose q equal to 0?
It happens that it is no more sensitive to the model, because if you put 0, you get 1. And
Exactly.
so the model disappears and you have no parameters and you have nothing to learn.
So
It makes no sense.
makes no sense. Okay.
Definitely not. And actually, what you get if you put q equal to 0, you get 1 always for any model, because it's the integral of a distribution, so you have 1. So, but it's important the asymptotic behavior. When q approaches 0, you are going closer and closer to the mode of the conditional mode of the function. This is just to say that, of course, changing the loss function, you are learning different things there. As I've told you, but the choice of what you want as a loss function is also related to how easy it is to optimize this loss function. And in this case, for instance, taking q equal to 2 is very easy to optimize. So this is usually why the square loss is chosen. From one side, because of course the conditional mean is a sound concept. For many distributions, pay attention that if you have Gaussian distribution, the conditional mean is equal to the conditional median and also to the conditional mode. So for the Gaussian distribution, the three constants are the same because the mean is in the middle. So split 50 and 50. And the mean is also the highest point of the distribution. So the mean, the median, the mode are all the same. But if you have different skewed distribution, of course the three concepts can be very different. Okay, so we have said we are considering hypothesis space with linear models. We want to consider empirical losses that are related to the square loss function. But again, the loss function with integrals over all the input space with the generative distribution P is impossible because we do not know P. And we do not have samples from X and T. And so, what happens? It happens that, of course, we have to replace this integral, okay, will be replaced by the summation over the samples. So this integral over the distribution P will be approximated by the summation over the samples. And here is where the problem appears. Because you'd like to minimize this one. And if you minimize this one, you are happy.